So the second part now will be first about databases. And a database is, well, a general definition would be that it's a collection of data stored in the format of tables. So you have a number of columns, which are the categories in the table. We have seen them also in the pandas data frames. And then we have the rows, which are the actually stored items, which has entries for each column. And it could look something like this one. You have two tables. One is animals and one is cells. And as you can see here, we have ID numbers, which probably corresponds to some animal. And here you have another column called animal. And when you do an analysis based on this database, you would probably mix the two of them and saying this animal has these and these features and it's identified by something. So here you can see that animal weights is in this table, and here is the more the measurement information or the characteristic information. Another thing is perfect. If you have typically student database and the classes as a typical example. So then you can see that you don't need to know about the student address to tell that a student is participating in a specific class. And then you only need a list of which students. If you want to know more about students, you can take the other table. And that is the kind of analysis you do within a database. And one typical language that is used for analyzing databases is abbreviation SQL, but it's pronounced SQL. And it stands for Structured Query Language. And it's essentially a universal language. It's as soon as you talk about databases, the next thing that comes up in your mind should be SQL. And it's used for searching, which is in that language called querying, and also to add information or inserting data into the databases. So there are different uses of SQL. Sometimes it can be used locally. For example, Firefox is storing all its preferences in a local little database. Then the engine is called SQLite, and that one is actually also easily connected together with the pandas data frames. So I have done some, for example, in my work, I'm looking at databases of experiments, and I want to make some statistics about the experiments. And what I'm doing is I'm actually pulling information out from the database to make counting how many users are using this kind, or how many days are using this kind of instrumentation, etc. And what I'm doing is then I pull all the information from the database into a data frame. My database is very small, so I can have everything in memory. Facebook is kind of the other extreme. Facebook has a huge amount of users, and they store all or some of the user information in a database. And they are using MySQL or something called Hive in order to make the queries in their database. So this is what is used in this context, and sometimes data is stored locally, like in my little case, or it can also be stored out on the cloud using supercomputers or something. Typically, when you do a query, you want to get the volume from cells. Then you select the column volume from the table cells. And the output of that is 1, 2, and 95. And then you may want to do some calculations on that, and you want to know the average volume of all cancer cells. Then you can say select, and then you apply the function average of the volume from the table cells where the type of cell is labeled as cancer. So if we go back to the small tables we had here, you can see that we had these two. That would be the type in the cell table. Then we can see that there is something, the volume is much less than the volume of a healthy one. And was it? Yeah, okay, yeah. It was 1 and 0.95, so this is the right value. And we could easily do all this directly. We could also do this using MATLAB, Python, R, Excel. But this is really a small example. But still, if you have the data stored in the database, you can actually do the computations directly using SQL commands. A little bit more advanced is get the volume of all cells in heavy mice. Then it gets a little bit more complex. Now we link the two tables. We have one called animals and one called cells. So here we select the volume from the cells table, and in the cases where animal, which has the same ID as let's see, as animal in the other table, animal here and ID here. So those two are related to each other. And then we check that the weight is more than 80. And that would give us then the volume of those cells. Actually, the volumes, it's not the average here. Then we can have more complicated things, looking for different tables and combine, doing joins, like inner joins, like the ones we had in the previous lecture when I talked about the databases. The same kind of join operations work also in SQL. And here we want to join the tables based on the ID in the animal table and the animal column in the cell table. SQL may be good, but sometimes when you go on very complicated queries, it can be complicated and it's not so easy to get the right answers. And also, if you want to do some network analysis, the query lines get longer and longer and more complicated, and it can be difficult to debug it. But it's getting harder and harder for those. And for that, there's NoSQL approach, which is not saying no to SQL, but saying not only SQL. And that is to create databases, database software, which goes beyond what SQL can do. And one is called MongoDB. And you can also start working, specify the problems in terms of graphs. So you can call them graph databases. And that would be going on the larger, more complex questions. So now we come back to our big again. So the big data and the definition. So one thing is big data is produced by velocity, a lot of data coming in, big amounts, and also maybe variety in the amounts. So we have a lot of heterogeneity. So we need something that is definitely performant, so we can really crunch the data, which is scalable. So you don't have to rewrite or change details for every new data type. And also flexible. If the kind of data changes a little bit, it shouldn't be too hard to change it. So the scaling shouldn't be a problem. We should essentially be able to do the same thing on 10, 100 or 1,000 times data amount. Your effort should be the same, but the effect should be that the computer, of course, will work a lot more. One problem is that you're starving for data, so you don't have enough data. And that can actually be a problem that you don't have enough interesting data, in particular when you have class unbalances in your data and you want to analyze it. It can be a problem that you don't have sufficient data in order to really make the right conclusions. Very important for the scalable and flexible is that you don't do any clicks per sample. So you have to have everything automated, and human interaction beyond starting the process should be brought down to zero. A little, say, real life story is that Google many years ago ran into this big data problem, and they had peta and exabytes of website data, and they want to collect information and make sense of them. And they have developed this algorithm called PageRank, and from that they want to evaluate the quality of different websites. And they could probably have used something that is available, but the question is how long time it takes. And in principle, what you need to do is to explore or traverse the whole database. So for every site on internet, check its rank towards this site. And that takes a long time. So you could have done that and divided on many computers and run it. But if you think about how many web pages there are out there, you would need quite some amount of computers. So they developed this page rank code, and it runs this little program for every site on the internet, computing some kind of page rank based on the current site, and compare this rank value to any other site in the internet. And after that, they get something together and get the current site rank. The complexity of this, as you can see here, you have a looping for over all internet sites twice, and that means the complexity of this is number of sites squared. Takes ages to do. So one way would be maybe to divide the sites, maybe in English sites, Chinese sites, and run this analysis on these separately. But now probably there are Chinese sites that have links towards an English site. What happens then? Then you have like two analyses in two separate little islands and no communication between them. So then you get in the problem. So buying a really big computer, the most powerful computer, one looping in this system would take months to do. And Google is doing this on daily basis. So it's not really working this way. So they need to have an efficient way of updating the page ranks. So, and then as we're talking about many big distributed systems, what happens if one computer or hard drive crashes during this work? Of course, we can have a backup computer and replace it. So that would be a backup computer for every single system. And no, then it would be extremely expensive solution. So maybe doing it a few computers within each hundred or thousands of computers, that's probably enough. So next problem is if there is an earthquake and all computers in a center goes down, what happens then? So what PageRank is doing, it's not only just counting, it's also taking old rankings. So if there is a loss of information, it can actually take those old rankings and fill them in as kind of an extrapolation of what the current status is. And with that, you can also iterate PageRank and until the ranks converge. So in the beginning, they probably are a little bit uncertain, but after a point, you get a pretty good PageRank for this analysis. One thing in this is to have something called MapReduce, which is a concept that Google claim, but other people say that, well, they had this idea before, but Google was the first one to do it at a scale beyond anything else. So again, considering the amount of databases available. And then what they did was to divide the tasks into two different main groups. One is map. That is something that works on individual data points. So here we have a vector of 1, 2, 3, 4, 5. And the mapping function is applied to each of these elements. So if we map this function to L, then we have the square of the elements. That would be the output. And that can be done completely individually and is fast to do. It's just increase the number of computers and you will have more fun. The other part is the reduce part, which actually takes information from different nodes and want to bring them together. So a typical reduce operation would be to have A plus B. So we have the reduce function, G of AB. That is the sum of the two. And if we want to reduce all the elements in this vector, then we have to call it first on the first two elements, then we do a new reduce on the next element, a new reduce on the next element, and so on. So it's kind of cascading down. This has shown to be a pretty efficient way, and you can probably also, depending on how possible it is to split it, you can actually split it into different parts. So the reduction can still be done in an efficient parallel way. So looking at, let's see if I can get my pen. So this looks like a pretty sequential chain, but instead you can have something like you have, oops, oh, that was an ugly one. Oops, you have 3, 1, 2, 4, 5. Then you can reduce those two, and those two, and those are reduced with this one. And all of a sudden, you only have 3 operations instead of 4 that I have here. So you can do it in this way. And that is easily parallelizable. So you can actually take each sub-branch here and delegate it to a different node. And in the end, there is a top node who is taking responsibility for the rest. And this is the more efficient way of doing the reduction. So looking at this reduce task, we have first partition all our input data into chunks across all the machines in the cluster. Then we apply the map, each element, and then we do some reshuffling, repartition or grouping of the data, and then we apply reduce on each group. In the end, we collect all the results and write to disk. And this is the way the MapReduce paradigm is working. So an example of that is key value pairs and grouping. And the example we're going to look at is counting words. So if we have something like this, we have a vector of some word, so a couple of lines with sentences. And the first mapping function is to split the lines into a list of words. And then afterwards, we can do some grouping of the words afterwards. The reduce adds up the values of each one. And the workflow would then be that first we have this vector of two lines, one with cat, dog, car, and one with dog, car, dog. And the mapping produces these small pairs where we have cat, count 1, dog, count 1, car, count 1, etc. Then the shuffling and regrouping, we see that there are many that are essentially the same. So we can see that cat is a list of 1, dog is a list of 3 ones, and car is a list of 2 ones. So, and then we come to reduction step where we do the counting itself. And then we see that there's 1 cat, 3 dogs, and 2 cars. And then we have done our work. A little bit larger counting problem. Now we take all the lines in Shakespeare's Midsummer Night's Dream. And let's first just import that one. And we get all some lines here out of that. And the next step, oops, I need to execute it. Now we do a serial execution, so the imperative, where we go through and check each line and count how many words there are in some dictionary. And that can be done. And the next step is to do the analysis of that. We do some sorting to count how many there are. We can see most frequent words and least frequent words. We can see that the is the most frequent word in Shakespeare's work. And then we have some really nice words here, which only have single counts. And in between those, of course, a lot of other words. Doing this in the MapReduce work, we need to define first some test function. No, it's a line to words function, which is the mapping. And there is even a little test code here to check that we are doing the right thing. And when we execute this, we can see that, okay, the unit test is doing well. We have, we're trying line of words, hi, I'm Bob, and out comes a sequence of words. Fine. Now we want to use something called a task bag, and a task bag is implements operations like map, filter, fold, and that is what we are going to use now in the Python. We have the possibility with these bags that they can actually work in parallel. So data is split up, splitting it up into multiple cores or even machines, depending on what backend you add on Dask. Could also be done on a graphics card, which you can see in the exercises of today's lecture. It can do iterating, so data is processed lazily, so it's essentially only defined what you want to do or can do, and then when some data is expected, the processing is started. And so now we want to build our bag for this word analysis. So first we create a bag from a sequence of all lines. We set some partition size, and then we see what the bag says. So it creates 13 partitions out of this data set. And now we want to do some map to the output. So the mapping is done on lines to words, which is then flattened. And the output is still nothing. It just says we have still a bag with 13 partitions, but it's not executed really yet. And now we want to do some cheating because we want to have the top and bottom. So we write some reduction functions, which is taking the counts from the data. In the top, you have the largest counts, and here we use the minus of the count. That means the largest value after that is actually a large negative value, and then the sorting gives you the top section. And when we run this, nothing more happens, just define some functions. And now we can run the analysis. Here I defined I want to have 4 workers. So this is now split up in parallel. And I'm running these two top 10 and bottom 10 as a compute with a certain number of workers. And now running it, you can see that we are running. And then we have the lists, and we get our top lists out of this. And if you look back on the previous slides, you can see that it's actually the same counts that you got before. And now we did this in parallel, so we can actually visualize it, how the computer was working with help of this diagram visualize. And then you can see how the cores are working. I have, or the workers are working. So we have got 8 workers that are doing stuff. So the first part is for doing the top count, the high score part, and that is the low score part. And they are running in parallel, each section here. Maybe a little bit different distributed, but that's it. Here you can also see what task is doing stuff and when it's doing it. And you can see here, some is doing, what is it actually? Flatten frequencies. Yeah, so it's calling some kind of operation called flatten sequences. And in the end, it's doing the collection. Now we can do the same again, just by changing here. On this computer, I have 8 cores, so we can see what happens. Execution time is actually the same in this case, which is interesting. And now if we run the visualize, you can see how it's distributed. And then we have divided the tasks on more workers. So one worker per each core actually now. So you can see how the tasks are working, and that can also help you to tune how your processing is working. You probably don't tune on the full data set, but you can take a sub data set and see how it behaves, maybe if there are bottlenecks, and what can be done on that. For distributed computing, there are a couple of different tools. And one is Hadoop, which is kind of a database framework. It was developed by Yahoo and is now released as an open source Apache project. All non-local data is copied over the network. Storage is automatically expanded with the processing power. And this is the way how many large companies like Amazon, Microsoft, Yahoo, Facebook deal with the huge amounts of data. And there is, let's see, no, I didn't put the link on it, but there was, there is a little YouTube movie where someone explaining the difference or the likeliness between Hadoop and the SQL, and how you make the queries in one or the other. Hadoop is usually based on that you need writing some JavaScript to access the data. But there is this Hive language which brings the Java into SQL commands, and that was pretty popular among particularly the Facebook people who didn't know Java programming, but they knew SQL programming. Then we have Spark is for distributed data sets again, but it also has a lot of algorithms built in for the processing. And well, it's developed by Algorithms, Machines and People's Lab at UC Berkeley back in 2012. It's a general tool that works with these directed acyclical graphs, DAGs, which I mentioned actually in the very first lecture. And it has a pretty coarse-grained processing, so simple operations are always applied on the entire set. And there is some in-memory caching that can handle this. It's a pretty good, easy specification, so you don't have to do the parallel computing can be done with a lot of logistics, libraries, or compiling. It's kind of a backend system that you can work with. And it's rather declarative than imperative, but so you can apply the operation F on each block in the image, or image or block. You can't tell computer 3 to wait for an image from computer 2 and perform an operation that is sent to computer 1. That's not possible using the Spark environment. So it's a more really massive declarative process. Results can be stored in memory or on disk, and it can also be specified to be redundant or not, depending on what you're doing. Then we have Dask. This is Python ecosystem. I actually already mentioned Dask before when I said we did these bags. And it's an easy way of bringing parallelism into your programs, because it's having interface to many different numerical codes like NumPy and SciPy, and also Pandas can work within the Dask framework. So now I will show a couple of examples. First of all, we have these DAGs, and they are more general than the MapReduce structure. And they're used actually in Spark and in Dask, and also in TensorFlow and PyTorch. So it's a pretty common use workflow. It's popular also then for the machine learning tasks. So it can be worked for either your local CPU, it can be used on the graphics card, it can be used on big parallel systems. And if you want to know more about this, you have a lot of links down here that tells that you can read more about this. Then there is a tensor comprehension system that Facebook has been using, for example, in this case, where they demonstrate how a piece of code, which you see up in the upper line, is expanded into something, and then it's split down into subtasks. And after the analysis, you have the code that you want to run on the separate nodes, which makes the most efficient execution. Now to go over to some DAG examples, we have a very basic one. And we create 2 images. We have one, all elements are equal to 0. The size of the image is 5 by 5, and the chunk is the same size. Then we do the same on with all elements equal to 1, and then same distribution. The graph of that one looks something like this, of the image A, or image 1, sorry. And then we want to do some arithmetics on that one. So we have image 4 is equal to image 1 minus 10 plus image 2 times 50. And that looks like this. So it's essentially looking like a normal code line. But if we look at what the graph looks like, we can see here that we have image block 1, image block. So there is only one image block, one called ones and one called zeros. Then we do some multiplication and we get same image size again. And then we have an addition operation. So that is what the network can look like. We do a little bit more calculations, and now we use some a multiplication between image 1 and image 4. And as we remember, image 4 is this expression here. So that is turning into a little bit more complicated network. And actually it's pretty stupid because image 1 is just zeros. So we multiply by zeros here. Doesn't really make sense, but anyway, just to show this example, how it looks like. So it can actually, this point is not computed before all that has been done. So let's look at an image processing example, how we can work with real images. And here we have a little example. We'll load an image with data, extract a little bit from it, and we look at what it looks like. And here we have a sum of all frames. You can see that's the bubbly data. And here we look at 10 frames only, stacked or mosaiced close to each other. We can also visualize the volume. And for doing this, I needed to install a new package. And here are the instructions you need to do. So you need to install ITK widgets. Then you have to tell Jupyter that to use a couple of extensions. And after that, you need to restart Jupyter. Otherwise, it will not work. And running this, we have afterwards this nice volume rendering of the network. Here you have a control panel where you can play with different settings. You can change the color map if you like that. You can also add slice planes in the data. So it's a nice viewer. That's an alternative to the other one I used back in a few lectures ago. So which one you choose and work with depends on what you like. So I think both works pretty well. Also, I think performance-wise, it doesn't need very much graphic card capability. I think it works on my 6-year-old computer, works on my 1-year-old computer, or 6-month-old computer. No problem. Both can visualize this. So then we want to create a DAG for the foam image. The image is 100 by 400 by 400. We want 20 slices per chunk, and we want to scale the intensities from 8-bit to a floating point value between 0 and 1. That we can execute, and we see here now the data is split down into several blocks because we had this chunk separation. Sorry. And now we want to add a filter operation, and now we use the Dask version of SciPy's and the ND filter, Gaussian filter. And in that, we can see that it looks essentially the same. And we want to flip the values and look at the graph for that. It's turning pretty big actually now. I need to go back. You can see here that the full graph is a pretty big one where we have split out the different images, and on each chunk now we apply a Gaussian filter. And now we also want to segment and erode, and of course the graph is getting even more complicated. We have some synchronization between different blocks, and there is some overlap between them, and that needs to be handled before we can do the final work. So it's getting a pretty complicated thing when you start running this in parallel. As soon as you have boundary exchange, it gets messy in the graph. And the final part would be to apply labeling, and that is we have to define a block label function, and that one needs to be applied on the eroded map. And let's run it and see what happens. We run here now. And right now we have 8 workers in this process. And well, it takes a little time to process it. And we can see now what the results look like. And here we have the process stack summing up again. Looks a little bit weird in a way, but it was probably what the blocks, how the blocks were segmented. And then you can see that there are different color codes in the different blocks. And they are actually, look like they have only one label, but it's because when you do this parallel coding and apply the labeling, you would have label 1 in all the blocks. So you would have items here, block 2, have an item here, and that one has another one. And all these would possibly get the 1, a 1, and a 1. So that would be that label 1 would be repeated in each block. So what we did in this block function was to add some scaling number. So we add an offset to each block, and with that block, we can have a nice separation between different blocks. And that is also the reason why we see this kind of very distinct coloring. If you look at each chunk for itself, you would see the differences in label values. The profiler output of that is looking like this. We have the 8 workers doing stuff, and you can see that it's the binary erosion that apparently did a lot of work. In the beginning here is the Gaussian filter. So the erosion apparently was a heavy thing. And let's see, can I slide or pan? Yeah, pan, I can. No, there is nothing more here. So the erosion seemed to be the hard task for the blocks in this case. And you can all see here how the CPU was used in this processing. And what you can do is to actually play a little bit with how many workers you are using. Many computers today are using, for example, hyperthreading. And if you have a large memory footprint, hyperthreading is not really beneficial always. If you have a lot of CPU load, then of course hyperthreading can be good. But if the memory footprint, that is how large memory blocks each process is using, then it may be that you can actually work with less cores and still have a good result, fast result, or even faster. So that is something that you have to balance and play with to get the right balance in the parallel code. Then there is also an importance of how you order your operations. So I'm going to show you 2 examples where we first select a slice and filter it, and then I filter the whole data, and then I select a slice. And the 2 examples you can see here. So you have a filter of, and that is just setting up the filter. Here you have the single slice, and where did I select it? Okay, I apply the filter slice directly here. And let's run this or define it. We say we have 4 workers, and we can see that the 2 approaches produce the same result, which is to be expected. But that one approach takes 3 times more time. So what happened here? That is what we need to find out. So if we select a single slice, the DAG looks like this. So it's split up in 3 blocks, apparently. And that means we can do the filtering very easily. But when you do the other way around, you have it divided into 10 chunks, and these need to work together. And finally, once all have worked, so you're actually filtering the whole image, and then you're taking out the slice from that. So a lot more work is done in filter and select a slice than select a slice and filter. So that is the reason for having this factor about 3 in this example. Last thing, one of the last things I'm going to talk about is cloud computing. And local resources, you can have them, but it's usually very expensive to build up a cluster. It's mostly not used fully. And also to manage this, you need have someone to manage and update and make sure, and usually it's dedicated IT staff. So depending on how large your group is or institute is, it can make sense to have make this effort, but not surely. And There is also the energy efficiency when you have a typical operating region. Typically, the power goes up linear somehow, and the energy efficiency is how much you really use of the computer. And that means you are running a lot of power for nothing, and that's not good. So what you can do instead is to work with cloud resources, for example, the Amazon cloud, where you can log in and you can buy the resources you need for your processing. Usually there is a kind of a free amount of processing time that you get when you start up, but then at some point you have to start paying for it. And depending what power you need, you have to pay more or less. So the high end nodes, they cost of course more, where you have many CPUs of good quality with backup from many graphic cards. That gives you a different options, how much you want to pay and how fast you want your results. So there is this Spark platform, which is heavily developed, and there are many available tools like k-means, matrix factorization, graph analytics, genomics, machine learning, etc. And there's a good commercial support for it. So many of these big companies, they donate a lot of funding for continuing developing Spark and its efficiency. And there are even a couple of startups. This was actually one of Kevin's slides, so it's a couple of years old possibly, but anyway, there are startups that get seed funding with a lot of money just for developing tools within the Spark environment. There's also a huge academic support. A lot of source code is available open source on GitHub. Sometimes the code that people have uploaded is much less than the PhD, the work that Kevin did for his PhD. There is also no patents or restrictions on use, and there is even a machine learning course in our department, which is based on Spark and how to work with it in machine learning. Finally, I come to some words about the future, how to work with this. And first of all, going beyond this would be to work on streaming. Until now, we have maybe assumed that data is acquired, stored somewhere, and then processed as post-processing. One thing is that our analysis should take weeks instead of months. Sometimes we want to do real-time analysis and statistics from the data. And one thing is that streaming, that data is coming in a steady flow. And sometimes we want to really analyze data in real time, at least to get a first grasp of what's happening. And for that, we really want to have the ability to use the same code that is used for real time as for the static evaluation. Of course, scalability, we need for covering faster real-time data flows, we need to connect more computers and just pop up more workers on those computers, and then we would keep up with the data rate. Another thing is that sometimes an approximate result is already a good indication. So if you're doing a real-time experiment, the full analysis may take a day, and you don't have that time, at least not to make a first qualitative judgment, is this experiment doing what it's supposed to or not? So you can say that compute the mean volume within some given time, or CI. Sometimes if you do real-time experiments, it's the only feasible solution. And maybe it's even the only way to do the analysis because the data amount is so big. And that brings me to the end of today's lecture. So I've been talking about parallel and distributed computing, databases, environments for distributed computing. And I see I have made a misspelling here. And I looked at distributed acyclic graphs, DAGs, and also went a little bit about talking about cloud computing. And well, this was the last lecture in this class, and I hope you enjoyed it. Next week, we are going to have the presentations of projects, and I'm going to send out an email with information about what is going to be done. And I also I will collect that and prepare next week's slides for that. Or actually just the web page, I believe. So that was all for today. So thank you for coming, and see you next week.